How's it going, guys? Today we're going to look at net ionic equations in both single and double replacement reactions. We're also going to be looking at writing complete ionic equations and talking a little bit about aqueous substances and dissociation. This is something that we did cover before we left for break, but there was a lot of confusion on it and it's been a long time, so I'm going to go ahead and go over it again here. So let's get started. The goals for today are to look at aqueous substances and their properties during reactions, and then learn how to write complete ionic equations and net ionic equations. So first, looking at aqueous materials, what is an aqueous substance? Hopefully you guys all remember. An aqueous substance is one that is dissolved in water. For covalent compounds, that's going to be determined by a combination of size and polarity, but we're going to be looking at ionic compounds today. And ionic compounds are almost always going to be soluble in water because of their differential charges. And often ionic compounds that are dissolved in water will dissociate. A completely dissociated compound separates down into its simplest parts. And in the case of ionic compounds, this means they're cations and they're anions. So here we see what happens when sodium chloride dissolves in water. We've got the sodium chloride molecule over here, and it's separated into the sodium cation and the chlorine anion. Down here, this is silver nitrate. This one, the silver is going to be the cation, and then the nitrate actually stays together as the anion. NO3 doesn't break down any further than that in water. This is a covalent compound, but it is the anion for silver nitrate as a substance. And there are a few nitrates, sulfates, chlorates, phosphates, there are carbonates, decent number of molecules that act like that, but hopefully it'll be pretty obvious. Basically, the metal is going to separate on its own. Over here, we see that this is hydrochloric acid. On this side, we haven't added water yet, so everything is dry. We just have HCl all bonded together, looking nice and the way it would normally look. Over here, however, it's dissolved in water, and as you can see, the hydrogens have separated from the chlorine atoms, so you've got your cation here, your anions here, and there's no longer that bond forming between them. If you would dissolve this water, evaporate it off by boiling it, you'll still get those HCl's forming back together, but when they're in solution, they're actually dissociated, they're separated from each other. So when you're trying to determine whether or not a compound is dissociated, ask the following two questions. First of all, is the compound ionic? Is it made up of a metal and a nonmetal? And second, is the compound aqueous? If it's a solid, if it's a liquid, or if it's a gas, it will not be dissociated, only if it is in the aqueous form. And so if the answer to both questions is yes, you will almost certainly have a dissociated compound. So on this next slide, we're going to go through a few practice problems, take a look at these, see if you can figure out which ones are going to dissociate, which ones are not, and I will go over it in just a second. All right, so first question, we're looking at MgO. First of all, is an ionic compound. Well, this is a metal, magnesium, this is a nonmetal, oxygen, so check, it is ionic. Second question, is it aqueous? This one we can see is solid, so it is not going to dissociate. Next one, sodium chloride. We've got a metal here, we've got a nonmetal here. That means that it is ionic. It is aqueous, so this one should be dissociated. Down here, we've got carbon dioxide. It is aqueous, so that's good, but carbon is a nonmetal, oxygen is a nonmetal. This is a covalent compound, so it is most likely not going to be dissociated. Here we've got magnesium sulfate. This is a metal. This whole group right here is going to be the anion. This is a nonmetal, and it is aqueous, so that checks both of our boxes. We've got a yes. And then this last one, AlCl2, aluminum is a metal, chlorine is not. It is aqueous, so it will be dissolved in solution. Now, dissociated compounds, when we have dissociated compounds in a chemical equation, they're going to occasionally cause some issues for us, so we need to be able to check for spectator ions. And spectator ions are ions that do not have any impact on a chemical reaction. Basically, they're called spectators. They're sitting off to the side. They're not doing anything. They're just kind of watching the reaction take place. We can only identify spectator ions by writing out a complete ionic equation. So we're going to look at how to do that right here. In order to write a complete ionic equation, you first need to break dissociated compounds down into their respective ions. So in order to do this, what we do is we look at this compound here. This is MgSO4. We've got a metal, we've got a nonmetal. It is aqueous, so we know it's going to be dissociated. In order to break that down, we have to break it into its component parts. So we know that magnesium, which is going to be our cation, It's going to have a 2 plus charge. And it is going to be with sulfate, which we know just because this is balanced, there's no charge here, this has to have a 2 minus charge, and both of these are aqueous. So that's how we'd break those down. Once we've broken down all of our dissociated compounds, we'll have the complete ionic equation. So on this next slide, what I want you to do is practice on your own, try to break all of these down into their respective ions. See if you can give that a shot. And for this one, I'm just giving you, these are all dissociated compounds. They're all ionic, they're all aqueous, so don't worry about that. Okay, so this first one should be pretty simple. We've got magnesium oxide, the Mg is the metal, the oxygen is the non-metal. So we get Mg2+. It is, of course, aqueous still, plus O2-, which is aqueous. Now, this is actually a very difficult compound to dissolve in water as far as ionic compounds go, just because that oxygen will readily react with the other oxygens to form oxygen gas, but we're not going to worry about that too much right now. This one, sodium chloride. Got sodium as our metal, chlorine as our non-metal. So we've got sodium, and we know if we look at the periodic table that sodium is going to have a charge of +1, plus chlorine, which is going to have a charge of +2. Now this one I wanted to throw in here so that we could look at a little bit of a different example. AlCl2, we've got aluminum is our cation, our metal, and chlorine is our non-metal or our anion. So we're going to have aluminum. And aluminum is going to have a 2+ charge in this case. Still aqueous. All of these should be aqueous. I probably should have written them up there, but I don't want to go back and do that. So, and then we've got chlorine here. Now chlorine has a charge of -1. And you could potentially just write out chlorine plus chlorine. You're going to be tempted to write Cl2 and put a 2- up here, but that's not actually how we're going to do it. What you need to do is put 2 in front of it, so you've got 2 chlorine ions, because those are going to separate from each other in the solution, so they're going to be actually spread out. Now, once we've done that, we can now write our complete ionic equations. So I'm going to walk through the first one, and then I want you guys to try the second one on your own. So the first one, got 2Na3PO4 aqueous. So sodium we know is a metal. This is a non-metal. Sodium, we've got 2 sets of these. Each one is going to have 3 NAs, so we've got 6 total NAs. And they're going to be plus. It's aqueous. Plus, we've got 2 PO4s. Now, if we have 2 PO4s, we have a 6+ charge here. We know that this PO4 is going to have a 3- charge. And that's just working backwards from the other side. Then over here, we've got calcium as our metal, and we've got chlorine as our non-metal. So this is going to be +3 Ca, and these are each 2 pluses. Get that from the periodic table as well. Plus, and then we've got 2 chlorines for each one. We've got 3 total, so we have 6 Cl-, and those are aqueous as well. Then that all yields, we've got 6 NaCl that is aqueous here, so these are going to be dissociated. We've got metal, non-metal, aqueous. This, however, Ca3PO4-, we still have our metal, still have our non-metal, but now it's solid. So this one is actually not going to be dissociated into solutions. So we can write this one as a solid, as is Ca3PO4-2 solid, plus, and then here we have 6 sodiums, Na plus, aqueous, plus 6 Cl-, and of course that is aqueous as well. All right. Sorry, the handwriting's starting to get a little bit bad. So go ahead and try the second one on your own. See if you can work through that, and then I will go ahead and go over that one as well. So for this one, we've got magnesium as our metal, chlorine as our nonmetal. It is aqueous, so it is going to be dissolved, or dissociated, sorry. So we got Mg, which is 2 plus we have 2 chlorines, which one is a minus. These are both aqueous. I'm not going to bother to write them out. It's going to take too much time if I write all of these out. So here we've got potassium, we've got carbonate. Potassium is our metal, carbonate is our nonmetal. We do have, it is aqueous, so we know that will again dissociate. We have 2 Ks. Each one of those is going to have a minus or a plus charge. Sorry. And then our carbonates, we've got 1 carbonate, which is CO3, and that has a 2 minus charge. Then on our product side, we notice that this one is solid, so it's not going to be dissociated, so we can write that out as is. MgCO3 solid plus, and then we have 2 potassium ions, which are still positive, and 2 chlorine ions. So that should be what yours looks like on that one. Now this is that same equation, just written over and much nicer handwriting, with all the aqueous is actually thrown in. And we're going to move on to the net ionic equation. So in this case, we can look and see what our spectator ions are. They are the spectator ions are going to be the ions that are the same in the reactant side as they are in the product side. So in this case, we can see that we've got 2 Cl minus on the left side, we've got 2 Cl minus on the right side, we've got 2 K plus on the left side and 2 K plus on the right side. We don't have the Mg2 plus on both sides, we don't have the CO3 2 minus on both sides, and we don't have the MgCO3 on both sides. So what's going to happen is these are going to cancel out, those are going to cancel out, and we'll be left with this as our net ionic equation. Mg2 plus aqueous plus carbonate 2 minus aqueous goes to MgCO3 solid. Those chlorine atoms and potassium ions or cations are both spectator ions. We don't want to write them into our net ionic equation. They just take up extra space. They didn't actually do anything. They didn't react during the chemical reaction that occurred here. So for practice, go ahead and try to write out the net ionic equation for this one right here. So walking through this one, we see that we've got silver nitrate, AgNO3. This is our metal, nonmetal, aqueous, so that's dissociated, metal, nonmetal, aqueous, dissociated. Got our solid here, and then we've got metal, nonmetal, and aqueous, so that would be dissociated. So writing this out, we're going to have Ag plus aqueous plus NO3 minus aqueous plus Na plus aqueous plus Cl minus aqueous. And that is going to yield AgCl, which is solid, plus, and then this one is dissociated again, so we're breaking it back down. We've got Na plus aqueous plus NO3 minus aqueous. Wow. So this is our complete ionic equation. We've got silver as a positive ion plus nitrate as a negative, plus sodium as a positive, plus chlorine as a negative, goes to silver chloride, plus that sodium ion and the nitrate ion. And as we can see, this ion is going to cancel, this ion is going to cancel, this, and we are left with our net ionic equation, which is Ag plus aqueous plus Cl minus aqueous yields AgCl as a solid. Right? Another example here, you've got lead chlorate plus sodium iodide. And all of these reactions are going to go ahead and be balanced for you guys. I'm not going to make you balance them on your own. So go ahead and give this one a shot. I'll go over that in just a second. All right, so to work this one out, first we need to separate our lead and our chlorate. So we've got Pb, which is a 2 plus. I'm just going to do A down here for aqueous from now on because I don't want to write that out every time. Plus, we've got 2 ClO4 minuses, which are aqueous, plus 2 Na plus aqueous, plus 2I aqueous. And that time I just had to write out the whole thing. Not really sure why. All right. Then on this side, we have lead iodide is a solid, so that's not going to be dissociated. The rest of them are. So we'll have lead iodide as a solid plus 2Na plus aqueous plus 2ClO4 aqueous. This is our complete ionic equation. We can immediately see these chlorides are going to cancel out, these sodiums are going to cancel out, these, and that leaves us with our net ionic equation of Pb2 plus aqueous plus 2I, that should be a minus by the way, minus aqueous goes to Pbi2 solid. This last one is a single replacement reaction. This is one we did in class with the aluminum foil in the copper chloride, and so it will undergo a reaction. We don't have to worry about the reactivity series, although you could use that to check and see that aluminum is in fact more reactive than copper. But go ahead, try this one out. So in this case, we're going to have aluminum as a solid on this side. It's not dissociated. It's as a solid. There's not an ionic compound. Can't break down any further than that. This copper chloride, however, is an ionic compound and it is aqueous. So we're going to have Cu, which is a 2 plus ion aqueous, plus 2Cl minus aqueous goes to, now we have copper as a solid, plus, and then this AlCl2, it is ionic, it is aqueous, so we're going to have aluminum, the 2 plus ion, it is aqueous, and 2Cl minus that are aqueous. Now in this case, aluminum solid goes to aluminum 2 plus aqueous, so that's not going to cancel. The copper 2 plus goes to copper solid, so that's not going to cancel. But this 2Cl minus and this 2Cl minus are the same. They're both dissociated in solution, don't actually react, so we're going to have those cross out. And this will give us our net ionic equation, which is Al solid plus Cu2 plus aqueous goes to copper solid plus aluminum, aluminum 2 plus, which is aqueous. And so what actually happened in this reaction is we had this copper, which is dissolved in solution. It was missing its electrons. It has 2 electrons missing because it is forming that cation. Aluminum as a solid, though, is in that solid form. Remember that metals have that, you see, I'm going to try to draw it over here really quick. The sort of sea of electron things going on. And so aluminum's electrons actually get donated to this copper, which makes this form a solid. And then because this becomes an ion and there's water around it, it will dissociate into solution, which forms that aqueous component there. So all you actually had happen in this was 2 electrons went from this aluminum to this copper, and that makes this copper come out as a solid. That solid aluminum gets dissolved into solution when it loses those electrons. And that's why that more reactive component has to happen. If this wasn't more reactive than the copper, then the copper would just shoot those electrons right back. It wouldn't accept them, and you wouldn't have this reaction go forward. So that's kind of trying to bring them all together. hopefully that makes some conceptual sense, but as long as you can do this actual ionic equation stuff, you should be good to go. There'll be a couple of practice problems with that on the classroom as well. That's it for today. I will see you guys next time.